A collision between two objects, we defined it earlier, typically lasts from 1 to 10 milliseconds. Now, I want to just play around with the math a little bit in how to convert milliseconds to seconds, and I'd like to do this very, very quickly. So we have 1 millisecond is one possibility, all right? The range would be approximately 1 millisecond to approximately 10 milliseconds. Now, one thing you could do is to convert the decimal form into scientific notation. Now, for the number 1, of course, it's a little bit silly, but let's just do it quickly, all right? 1 times 10 to the 0 would be 1. Okay, that's in correct scientific notation. 1 times 1, 10, anything to the 0 power was 1. 1 times 1 is 1, that's 1 millisecond. 10, all right, to convert this to scientific notation, we would move the decimal to there, all right? And so in scientific notation, 10 milliseconds would be 1 times 10 to the first milliseconds. All right, now, one way that you can convert milliseconds to seconds, well, let's call this the prefix method, all right, where you recognize that the prefix milli, all right, milli means 1,000th, or 10 to the negative 3. That's what milli means, all right, recognizing what the prefix milli means. So instead of milli, we put 10 to the negative 3. So 1 times 10 to the 0 times 10 to the negative 3, that's instead of milli, and the seconds come down. All right? This one, 1 times 10 to the first and 10 to the negative 3 in place of milli, and the seconds are still there. So what would this be? How many seconds would this be? Well, when you multiply exponents, when you multiply exponential numbers, you add the exponents. So 0 plus a negative 3 would be 10 to the negative 3. So in seconds, this would be 1 times 10 to the negative 3 seconds, or 1 millisecond. Okay? Now, this one here, all right? 10 to the first times 10 to the negative third. When you multiply, you add the exponents. 1 plus negative 3 is going to be 1 times 10 to the negative 2 seconds. All right? So that's one way, using the prefixes to convert milliseconds to seconds. All right? One other way to convert milliseconds to seconds would be what we call the factor label method, and I did that earlier. Let's do it one more time. The factor label method. This, by the way, is very, very similar to what we call dimensional analysis. Very similar concept. All right? So, prefix method, right? Milli is a prefix. It means 1,000th. Factor label method. Now I'm going to show you the factor label method. All right, so back to, let me erase all that. All right, remember that the answer that we got here in seconds was 1 times 10 to the negative 3 seconds. The answer that we got here was 1 times 10 to the negative 2 seconds. All right, now let's take 1 millisecond. Let's do the factor label method to convert it to seconds. All right, now notice how this is on top, this is on the bottom. Top, bottom. That's why you have a big set of parentheses. I put the number here, and then this corresponds to the top, and down there is the bottom. I want to get rid of milliseconds, so I put milliseconds on the bottom. They're going to cancel. That's why I put milliseconds on the bottom. I want seconds. All right? Now, top and bottom have to equal each other. One big giant second is equal to 1,000 little milliseconds. So this is 1 divided by 1,000. All right, take the 1, and to divide by 1,000, you're going to move 1, 2, 3 places to the left. So it's going to be 0.001. All right? So 0.001 seconds. That's seconds in decimal form. To put that into scientific notation, move the decimal 1, 2, 3 places to the right. And so what you get here in scientific notation, all right, 0.001 seconds in correct scientific notation is going to be 1 times 10 to the negative 3 seconds. All right? Now, 10 milliseconds, factor label method. Convert this to seconds. All right? Get rid of the milliseconds. Milliseconds top, milliseconds bottom, cancel. The milliseconds are going to be gone as soon as we put the correct numbers in. Milliseconds to seconds is what I want. These two numbers in the parentheses have to equal each other. 1 second is 1,000 milliseconds. You're taking 10, you're dividing it by 1,000 because the thousand's on the bottom. Remember, the equal signs are over here, so you cannot cross multiply. The only time you can cross multiply is when the equal sign is in between. The equal sign's over there. So this is 10 divided by 1,000. We're going to take 10, we're going to divide it by 1,000 by moving it 1, 2, 3 places to the left. It's going to be 0.01. All right? So we're getting 0.01 seconds. What would that be in scientific notation? Move the decimal until there's one number in front of the decimal. It's going to be 1 times 10 to the negative 2 seconds. All right, so whether we do the factor label method with these parentheses, or we look at the prefix and the meaning of the prefix, you're going to get the same answer. It's two different methods for converting milliseconds to seconds. In the case of 1 millisecond, it's going to be 1 times 10 to the negative 3 seconds. In the case of 10 milliseconds, it's going to be 1 times 10 to the negative 2 seconds. Okay? Just a little bit about converting milliseconds to seconds. Two different methods. What's the meaning of the prefix or factor label method? At this time, you're going to pause the video for 5 minutes. You've got 10 problems converting milliseconds to seconds and seconds back to milliseconds. It doesn't matter what method you use. You can use the prefix method, you can use factor label method, you can do it in your head. I don't care, just get them right. You've got 10 problems, take about 5 minutes, pause the video, and then pick the video right back up again. Now, how long a collision lasts, in other words, the duration or the time interval, depends upon the materials that the two objects are composed of, which determines whether the objects have the ability to deform and spring back, which lengthens the time they are in contact. So what we find is that hard objects, like 2 pool balls or 2 steel balls, or a hockey puck and a hockey stick, objects that are hard, tend to collide in a very short amount of time, on the order of perhaps 1 millisecond, because they hit and they don't squish, they smack off of each other very, very quickly. Now, soft objects, like a baseball or a soccer ball, objects that are soft, when they contact, they tend to squish into each other and then spring back. And all of this squishing and springing, kind of like a spring or a slinky, takes more time. So that when softer objects collide, the time of contact tends to be more on the order of about 10 milliseconds or 20 milliseconds, something more like that. All right, so we have hard objects bouncing off quickly and softer objects colliding and bouncing off of each other, taking a lot more time. So, how does an impulse work in real life? And how do the interchange of force and time to the impulse work in real life? A great example of this would be the seatbelt or the airbag in a car. All right, now, I'm going to prove to you in a later video that the impulse on a driver in an accident is the same regardless of whether the driver wears a seatbelt or not. So if the impulse is the same whether the driver wears the seatbelt or not, or uses an airbag or not, how is it that people's lives are saved by using seatbelts and by using airbags? Well, keep in mind that the force and the time both contribute to the impulse. Now, think about what happens if you're not wearing a seatbelt or you have no airbag. All right? What happens when the car screeches to a stop? Your body very quickly hits that dashboard. All right? So the time is very, very small. Let's say on this side, this is the side without the seatbelt. No seatbelt, no airbag. The time to hit that dashboard is very, very small. 0.002 seconds, let's say. 2 milliseconds. So if the impulse is 4 Newton seconds and you're hitting that dashboard in 0.002 seconds, the force on your body is 2,000 newtons. Right? That's relatively high. It's a large force. It's going to do some damage to your body. Now, what happens when you're wearing a seatbelt is that the seatbelt, the car comes to a stop in the crash. The seatbelt is pulling on you, so it takes longer for you to come to a stop. It takes longer for you to hit that dashboard or to just come to a stop. So the time is increased. Same thing with the airbag. All right, the airbag, if this is you and this is the airbag, all right, then you're pushing into the airbag. The airbag is slowing the amount of time it takes for you to come to a stop. All right, so the amount of time increases with a seatbelt or an airbag. So let's say over here again, and I will prove to you in a later video that the impulse is the same, all right, but given that the impulse is the same, 4 Newton seconds, if it takes longer for you to come to a stop, let's say 0.008 seconds this time, look what happens to the force. The force on you is less. So less damage is done to your body when you wear a seatbelt or if the airbag deploys. All right? So again, the relationship here between force and time is an inverse relationship. Keep in mind, all right, I'll just use this one. When force is over 1 here, all right, same thing over here. When one quantity is on the top and the other quantity is on the bottom, on opposite sides of the equal sign, all right, they are inversely related. All right, so when one goes up, the other one goes down. All right, that is an inverse relationship. When the time goes up, given if J has to stay the same for everything I'm talking about, if this one stays the same, this one goes up, this one goes down. Again, that is an inverse relationship between force and time. Now, another example of the inverse relationship between force and time, a boxer. A boxer is trying to maximize the force when he punches the opponent. He wants to do more damage to the opponent's face or upper body, whatever, all right? So he wants the force to be greater. So he wants the time to be as fast as possible. So the boxer isn't going to go hit the opponent in the face. All right, let's say this is the opponent's face, this is the boxer. The boxer isn't going to take a long time to hit the opponent in the face, right? Because if the time is increased, the force is decreased. The boxer is going to hit the opponent very quickly. Wham! Okay? And the decreased time that the boxer's punch is in contact with the other guy's face, bam! The increase, there's an increase in the force. And again, the impulse is going to be the same in that situation. So the boxer should be fast, wham! And not slow, wham! No effect. As we stated earlier, a collision is defined as a relatively large force which acts over a relatively short period of time. Examples of common everyday collisions would be a hammer hitting a nail, a foot kicking a soccer ball or a football, a baseball bat hitting a baseball, a bullet hitting a glass window, a speeding bullet hitting a glass window. Collisions and explosions are examples of impulsive forces. Explosions would include a firecracker going off, a cannonball being fired out of a cannon, etc., etc., etc. Now, what I'd like to do here now is go into more detail about the graph that we started to draw earlier. All right, remember, when you are kicking a ball, like a soccer ball, for example, all right, no force until your foot contacts the ball, then a small force when your foot first contacts the soccer ball, and that force increases as your foot pushes into the soccer ball. So again, no force until contact, then at contact, the force starts to increase. In this case, we're going to stop at about a force of 300 newtons. You see force in newtons on the y-axis. You see time in milliseconds on the x-axis. Now, once you reach maximum force, all right, now keep in mind that my force is imparting velocity to this ball. This ball is going to start going that way. So maximum force, and now the ball starts to deform, and it's also starting velocity in this direction, okay? So that force is now decreasing back down to 0, all right? So here's that maximum. Now we go back down, oops, let's make that a little more symmetric, okay? Something like that. Much better, okay. We're trying to make it as symmetric as possible, all right? And then back down to 0, okay? Now, the only way to absolutely accurately calculate the area under this curve would be to use calculus. We're not going to do that, all right? Keep in mind how you determine the slope of a graph, the meaning of the slope, and how you determine the meaning of the area under the curve. The meaning of the slope you would determine by looking at your y and looking at your x and saying, well, y divided by x is going to tell me what the slope means. Well, force divided by time, all right? Oops, I'm out of my frame here. Slope, right? Y, force divided by time, means nothing. So the slope of this graph, has no meaning. Force divided by time, there's no equation you're going to find that has force divided by time. It means nothing. But what about the area, right? Force times time has a meaning, all right? The area, all right, force times time, on this graph, force times time, the meaning of the area is impulse. All right, so the area is impulse. But again, we cannot easily accurately calculate this area because it's not a rectangle or a triangle or a square. We would have to use calculus. We're not going to do that. So this is where average force comes in. Well, if the force is 300 here, then and 0 down here, then the average force is somewhere around 150. All right, so here's my original drawing, right, my original curve. Okay, we can make that a little more symmetric. Let's try to make that a little more symmetric. Okay, a little better. All right, so now an average would be something like 150, right, stretching from 20 milliseconds to 40 milliseconds. The duration of time stays the same, and the average force, right, is about 150, right, between 100 and 200. So we'll put that right about there, all right, and your average, all right, is going to be this area, which is easy for us to calculate. All right, so that's force average. All right, so let's calculate the force, the impulse here. All right, we're going to calculate the area under under this line right here, the area of this rectangular box. All right, the force times the time. All right, so the area is going to be J equals force times time. The average force is 150 newtons. All right, the time is 20, from 20 to 40, all right, is 20 milliseconds, right? If it was from 10 to 30, that would be 20, right? If it was from 20 to 50, that would be 30. This is between 20 and 40, that's 20 milliseconds. And remember that 20 milliseconds, all right, 20 milliseconds, converting that to seconds, all right, we're going to divide by 1,000, all right, 1 second. So if you divide by 1,000, that's going to be 1, 2, 3, all right, 0.02 seconds is what you've got there, all right? So all you're doing is finding the area of this rectangle. The force is 150, the time from here to here is 20 milliseconds, all right? And that means that your answer, all right, let's see what we've got here, 3 Newton seconds. Okay, that times that, pick up your calculator, 150 times 0.02 is going to be 3 Newton seconds. Your impulse, all right, is about 3 Newton seconds. So what we've just done is used an average force to estimate the impulse of this oddly shaped curve here. All right? So that's why often when they're doing a question on a test, they're gonna give you the average force instead. So don't worry about it. Just put average force up into the impulse equation, just the same as you would if it was if it just said force. All right? Don't fret too much about the word average force.